Okay, so we're going to actually cover all three sections of Chapter 4 today, believe it or not, in the mere 40 minutes that we have left. And I think it should be basically no problem. There might conceivably be a little bit of streamlining at the end. We'll see. So 4.1 is very, very quick. The main thing to talk about is the generalization of the idea of Taylor polynomials. So, quick reminder from Calc 2, this is what a Taylor polynomial looks like, right? So there's a, general formula for the terms, and you just keep adding more terms as the further you want to go out. The point to this is that this is a polynomial that mimics the function that you're approximating. Specifically, it's the polynomial that has the same value, the same derivative, the same second derivative, et cetera, all the way out to, whatever the degree of that polynomial is. And so by sharing as much in common with the function, that's how we say that it's mimicking the function. Okay, so the multivariable version of that is to have a polynomial that mimics the multivariable function in the sense of having not only the same value, but all of the same partial derivatives and second partials and third partials, et cetera, all the way out to, whatever the degree of the Taylor polynomial is that you're talking about. Now, there are more derivatives here to be mimicked, right? Because, for example, there's only a single first-order derivative in single variable calculus. There's several first-order partial derivatives to be mimicked. So it's more constraints, but nevertheless, it's really an equivalent set of requirements. So here's the answer. You don't have to derive it yourself. Here's what it is. Now, we're only going to look at the degree 2 Taylor polynomial, but here's the formula. F of A, derivative times x minus a. Notice that's very similar to the single variable version. Now, of course, here the derivative is a matrix instead of a just, f prime. And it's being multiplied matrix vector product times the vector x minus a. Sure, it's a different appropriate to the context, of course, but highly analogous. And even this second order term is pretty analogous. Notice that there is what you might call a second derivative. Here, the second derivative takes the form of a matrix of second partials. This is called the Hessian matrix. Just terminology. There's two factors of x minus a, just like in the single variable version, and then there's this scalar factor of 1/2, just like in the single variable version. So it's all very analogous. Okay. All right. Now, the main thing that we're going to do with these is make use of the Hessian matrix. And exactly how we're going to use that will reveal itself in the next section when we talk about the second derivative test, the multivariable second derivative test. So that said, this is really most of what section 4.1 is about, is Taylor polynomials. Much of 4.1's presentation of which is review of single variable Taylor polynomials. So we're done with section 4.1, right? So I told you we're going to be able to power through pretty fast. It's not that much going on. Okay, so optimization. How do we find where a function's as big as possible? Starting with a real quick review of single variable optimization. And single variable optimization, if you have an interval, and on that interval you want to find the maximum value of some function, and I've drawn here the graph of some function. This is kind of a hypothetical, so I can point and draw pictures. Then here's what I'm going to call the main tool for single variable optimization, and this is what I'll call an elimination tool. This is a set of criteria which, if satisfied, allow me to eliminate a candidate point as being a possible maximum. For example, let's think about this point right here. That point being in the interior of the interval, presumably, for the purposes of this example, the function is differentiable there, so we can do calculus. And let's suppose that the derivative is non-zero, as the graph kind of suggests that it is. That being the case, I claim that there is no way that could be a maximizer. And the big idea as to why is, well, look, the function is in the process of increasing, right? If I were to go to the right here, and I've got room to start moving to the right because I'm in the interior of the interval, as I move to the right, you can see it right there in the graph. The function is in the process of increasing. This couldn't possibly be the biggest value of the function because it's even bigger right next door. Right? Does that make sense to everybody? So, and now let's look at a different example. Let's look at, let's find this point over here. Now at that point, the derivative is negative, and it's tempting to say, well, if I move to the right, the function's not increasing, the function's decreasing. True, but if I move to the left, which I can, because I'm in the interior of my interval, as I move to the left, the function is increasing. And again, this therefore cannot possibly be the maximizer that I'm looking for. Right? So whichever direction you have to go to make the function increasing, hey, whatever, right? But the point is, when these conditions here are satisfied, then that is not the maximizer you're looking for. And we eliminate it as a possible max. Now, good news, this applies almost everywhere in the domain, practically every point in the domain. There's precious few counterexamples in this domain that don't satisfy all three of these conditions. So the boundary points, right, they're not in the interior. Let's see here, points where the function fails to be differentiable. So here you go, there's a value of x where the function's not differentiable. Right? Points where the derivative fails to be non-zero, aka where the derivative is zero. Okay, well that's here and here. So at these points, my elimination argument fails. I can't say for sure that these aren't maxes, nor can I say for sure that they're not mins. I really don't know what's going on at these points. I just can't eliminate them, right? So we call them critical points with the idea that these might be what I'm looking for, and I'm going to have to resolve the matter by other methods, and we'll talk about that, a little bit down the road. So good news, though, the elimination argument eliminates all of the other points. So all of these points and all of those and all of those and all of those, definitely not what we're looking for. Okay, now this is a particular take on single variable optimization. Is everybody happy with this? Does that all look familiar, I hope and presume? Okay. All right, well, good news. The multivariable version of this is morally equivalent. Here it is. Let's suppose you have a domain. This time our domain is a two-dimensional region in the plane. So this is going to be a two-dimensional multivariable optimization. If you have a point that satisfies these three criteria, then I claim the function is in the process of increasing and therefore could not possibly be what we are looking for. Let's see some specific points. So in fact, let me get back to the green just to be consistent. Let's look at this point right here, for example. That point, it's in the interior, meaning that from that point, I'm free to move whatever direction I might want to for whatever reason. The function is differentiable at that point. Okay, now again, you can't really tell from the picture, but I'm going to presume differentiability as vaguely implied by the picture, but assuming that it's differentiable. And I can even kind of infer what direction the gradient is sort of pointing, because again, use your imagination, at kind of on the side of a hill there, and uphill would seem to be kind of like that toward that mountaintop up there. And so I'm going to say that the gradient's probably vaguely sort of about like that. All right. So these three conditions being satisfied, well, the function is in the process of increasing. Specifically, the function is increasing as I go in the direction of the gradient vector. Function's getting bigger. This couldn't possibly be the maximizer we're looking for. It's still getting bigger. Everybody see how that works? It's morally equivalent to what we did here in single variable. Okay. All right. So again, these three conditions are satisfied almost everywhere in our domain. Vast majority of the points in the domain. So now, there are arguably more problems. Most noticeably, the boundary is now an entire curve of points. It's not just 2 points. It's not just 2 endpoints. And that's a problem. We're going to have to figure out how to deal with that. We'll get there in a few minutes, later today. Let's see, points where the function fails to be differentiable. Well, again, most of the time, that's not really a problem. Most functions that we write down are differentiable, right? All polynomials, differentiable everywhere. Exponentials, differentiable everywhere. Trig functions, log functions are differentiable wherever they're defined, right? So, most functions you can kind of at a glance just look and see if they're differentiable everywhere, and if they're not, it's usually pretty clear where there's a problem. Okay. And then now let's also look at where the gradient is equal to 0. In other words, where the gradient fails to be non-zero. Right? Well, let's see here. Here's one. Right? The gradient is kind of flat up here at the top, if you will. It's also kind of flat here at this sort of mountain pass at that point. And it's also kind of flat. There's sort of a little mountain pass of sorts there as well. So at this point. So let's see here. Other than those points, everything else is eliminated. Right? Our elimination argument applies everywhere other than those few points. Which, again, as before, we call critical points because we don't know what to do with them. Is that fair? Everybody okay? All right. Okay, so let's see how this works in practice. Here is a function of which we want to find the critical points. We're going to look at our rules for critical points. Critical points, we've got to first check and see if there's any boundary points. Then we've got to find points where the function might fail to be differentiable. Right? If there are, those are critical points too. And then we're going to take the gradient and set it equal to 0. Okay, off we go. What's the boundary here? Well, this function's defined for all values of x and y. It's polynomial. It's defined everywhere. So there is no boundary. So therefore there are no boundary critical points. Does that make sense? Right, sometimes it's easy. Right? Okay, where is there a failure of differentiability? Well, nowhere. It's a polynomial. Polynomials are differentiable everywhere. So we don't have any differentiability failures either. So, okay, no luck there either. Okay, lastly, we take the gradient and set it equal to 0. That's our third avenue for finding critical points. So that would tell me that this would have to equal to that, and this would have to equal to that. The latter of which immediately tells me what y is. Y has to be 0. There's no way around that. And then the former of which tells me x could be either plus or minus 1. So all together, I get these critical points. Negative 1, 0, and 1, 0. How are we doing? Everybody happy with that? All right. Cool. All right. Now, the algebra on this one was easy. There are some landmines, algebraic landmines, to be careful with. That's the purpose of this example. Now, don't worry about what function this may or may not have come out of. But let's suppose this was how the vector algebra worked out, and I needed to solve this pair of equations that, that's equal to 0, and, this is equal to 0 too. How do I solve that? Well, this green equation tells me x squared has to equal to y squared, and here's where students very often make a mistake. Very often students will cancel the square or, something like that, right? And then just say, okay, well, that means that x must equal to y. And no, it must not. It is not must. Anyway, it is not the case that x must equal y, right? There are two possibilities, and either of these possibilities is just as good as the other, right? You cannot just, I like the one where x equals y better, because it doesn't have to. It could be either. So what we have to do here is we have to break this down by cases. I've got to look at the x equals y case, and then separately, I have to look at the x equals negative y case also. You have to look at both. Otherwise, you will miss critical points. And of course, that's bad. All right, so let's see how this algebra works out, starting with x equals y. If x equals y, well, plug that into there. That equation turns into this, which is easy to solve for y. And once you know y, then of course, that tells you x, which gives you your critical points. How we doing? Everybody follow all that? I whipped the lines around there pretty quickly, but just not that much algebra. So, okay. So we found two critical points. Now, again, this is where a lot of students would draw the line and spike the football on the 2-yard line, as it were, because we also have to check where x is negative y. If x is negative y, that will turn this equation into that, which is different algebra. If I got different algebra for y, I'm going to find different values of y. You'll see here are literally different values of y. And then furthermore, not only do I get different y's, but I'll be plugging those different y's into a different formula to relate to x. And so I get different critical points here. All right, so all together, these are the ones that most students will find, and these are the ones that a lot of students will miss. Arguably, we don't need to talk about the 0, 0. Again, we found it already in the first, but certainly many students will miss this critical point down here, and that's not good. How are we doing? Is everybody happy? Okay. All right. Okay. So heads up with that algebra. Second derivative test. This is while we were looking. Oh yeah, question.
We're solving these simultaneously.
Yep. Did I?
Yeah.
Oh, okay. Yep. Yeah, absolutely. Yeah, we have to find points that satisfy both of these equations at the same time. That's right. Yep. All right. The reason we were talking about Taylor polynomials in section 4.1 is because the Taylor polynomial is a way to motivate the second derivative test. Here's the single variable Taylor polynomial, and of course the behavior of the second order term is controlled very largely by, that second derivative. If it's positive, then this second order term is always positive. If it's negative, the second order term is always negative. It all comes down to whether that second derivative is positive or negative. Okay, what about the second order term in the multivariable Taylor polynomial? This is a quadratic form. This is not sort of just a product of scalar factors, nice simple thing like we had in the single variable case. This is a sophisticated object of linear algebra. This is a problem, right? What we need to know is whether this quadratic form is positive definite or negative definite or indefinite. Right? I need to know whether this term is always positive, in which case, if you think about it, if that term's always positive, then we're talking about a concave up graph, which means that my critical point's a local min, or vice versa. Okay. So, y'all may recall there were some rules about quadratic forms in how to know when they're positive, definite, negative, definite, etc. from Math 218. But here's the thing. We know more than just that this is a quadratic form. This is also specifically a quadratic form where this matrix defining the quadratic form is symmetric. Because mixed partials are equal, right? Assuming the appropriate regularity. Right? So it turns out that quadratic forms, when you have a symmetric matrix, there's a little bit more that you can do. And this is I'm going to call it a challenging linear algebra exercise. If you're interested, feel free to try to, piece together. This is kind of the major landmarks along the way. But knowing that it is a symmetric matrix, we can rewrite the rules for positive definite and negative definite. And here's the punchline. Here's what it all boils down to. This is all you actually really need to know about the second derivative test, is this little flow chart. And make sure to memorize this little flow chart. You do need to know this little flow chart. So here's how it breaks down. It's kind of weird. But here's the deal. If your Hessian determinant is positive, then in some sense it's all exactly as you would sort of expect. The XX second partial positive means local min and negative means local max. Just like in single variable. Right? So a positive Hessian determinant means good news, everything's exactly like you would expect. Okay. Now, that of course is not a given. It is also entirely possible you will have a negative Hessian determinant. If you have a negative Hessian determinant, you have a saddle point, aka a Pringle point, right? It's sort of concave down in one direction, kind of concave up in the other direction. You will have a saddle point of some sort. Who knows what kind of a saddle point? No comment, right? But if that Hessian determinant is negative, it's definitely a saddle point. Okay, and then there's a third possibility, which is your Hessian determinant could be 0. And if that happens, the test fails. We throw up our hands. We have no idea. We cannot classify such points with the second derivative test. Okay, so make sure to know these rules. Here's an example of how to use those rules. We're going to look at this function here, of which we've previously found these critical points. So let's test them real quick. Notice in order to do so, we're going to need to know the Hessian matrix, various partial derivatives. We're going to need to take the determinant of that Hessian. There it is. And now we play the game. We're just going to follow the flow chart. Starting with this first point. Plug it in. Hessian determinant's negative. Saddle point. Game over. Definitely a saddle point because the Hessian determinant is negative. It's following this rule right there. How are we doing? Is everybody with me? All right, let's look at the second one. Looking at this point right here, plug it in to see what the Hessian determinant is. Let's see here. That works out to be positive. That takes me up to here, which tells me I need to look further. I need to know about the XX second partial. That's my top left entry in the Hessian matrix. Now, is that positive or negative? Now, okay, fine. I got to take my point here then. Same point. Plug it into there. And what I find is that FXX is positive. Positive means local min. So that's a local min. Everybody see how that works? It's plug and chug. Okay. Cool. All right. Well, Now, there's a few more things that we could say if we had time about Section 4.2. These pages here, though, are supplemental. These are not essential. Global extrema is not something that we're going to really make part of the course. If you want to look at this for your own personal feeling of thoroughness in the subject, feel free to give it a glance, but it's not something that you're required to know. And likewise, all this business here about how to check the boundary, this is ultimately what we're going to find to be a highly suboptimal method. And you can glance at it if you'd like, but it's really not important, and don't feel the need to look at that either. So basically, these next two pages are to be skipped. And we move on now to Lagrange multipliers, section 4.3. All right, so we're making pretty good time here. So this gets to boundary issues. How do we check that boundary? Boundaries are what we're going to call a constrained optimization problem. And let me describe what I mean by constrained optimization. Constrained optimization, for example, this question right here. There's a function I want to maximize. A function I want to optimize. It says I want to find points closest to the origin. That means I want to make distance squared, might as well, as small as possible. So I'm looking for a minimum value of distance. Nice little mathematical life hack. If you want to minimize distance, you can also minimize distance squared. It's the same thing. It'll give you the same answers. Right? It's a nice little hack. It avoids square roots. Nobody likes square roots. So that's what we're trying to minimize in this case. It's called the objective function. But notice we have a constraint. I'm not looking at all points in the plane. I'm looking only at points that satisfy this weird equation. Okay, some points count and some points don't. How do I deal with this? We're going to call this the constraint. More specifically, notice I've got this written as a level set of a certain function. The function whose level set I'm looking at is called the constraint function. Now, this arrangement where we understand the question, the objective and the constraint by way of each being represented by a function. Right? We need a specific function to optimize. We need a specific function whose level set, it's got to be a level set, is your constraint. That's how we're going to approach all of these constrained optimization problems. So what that means is that if your algebra comes to you by way of an equation that's not already written as being, stuff equals constant, then you've got to move terms around however is necessary to make it stuff equals constant, because it is, again, part of the rule. The way we're going to approach this, I need to be talking about a level set. That's what we're going to need. Okay. All right, some other examples. Here's a very natural question you could ask. What's the biggest rectangular box that I can make, given that I'm only allowed to use a certain amount of surface area? Right, so maybe cardboard is getting expensive these days, and you within the budget you can only use a certain amount of cardboard, otherwise it's going to cost too much money. For that given amount of cardboard, you want to make the biggest box you can, perhaps. Right? So the optimization problem is that what I'm trying to make as big as possible is volume. And my constraint function, the thing that has to be a constant, the thing of which I'll be looking at a level set, is the area function for that box. Does that make sense to everybody? Another real-world scenario. Suppose you're starting a small business, and naturally you want to maximize productivity. Okay, well then that's our objective function. We want to be as productive as possible. We want to be able to we want to be able to produce as many widgets as possible, right? Well, here's the thing. I only have a finite amount of money to spend. The bank would only give me a loan for a certain amount. That's all the money I have. So from that same budget, I've got to hire my labor. I've got to hire I've got to buy all of my tools and machinery. I've got to buy the materials that will make up the widgets that I'm making, right? And the more labor I buy, the less I have left for materials, etc. Right? So my constraint is the budget. The budget is fixed. The budget is constant. So money spent on labor plus money spent on tools plus money spent on materials. That function must be constant. That's my constraint function. How are we doing? Is everybody on board? Okay. All right. So there's always going to be an objective function and a constraint function. All right. What do we do with them? Here's the key tool. It is an elimination argument, just like in the unconstrained case. I claim if these three things happen, then the point you're looking at is not a maximizer. Roughly speaking, here's the picture. If you have a constraint set, keep in mind a constraint set is always a level set. That's the rule. That's the premise that we're starting with here. Furthermore, remember that level sets are always orthogonal to gradients. So my constraint gradient is always orthogonal to my constraint set. And if that's the case, and now I do need for that constraint gradient, by the way, to be non-zero. So, if it's zero, then it doesn't define a direction, and that's awkward algebraically. If my objective gradient is off-axis, like so, in other words, if it's not a multiple of my constraint gradient, well, this is clearly not a maximum. At a glance, look, there's no way that this is the biggest value of the function. Look, the function is getting bigger as I go in this direction. The gradient of f is leaning this way. If I kind of, within the surface, just kind of follow that gradient, you can look at this angle. That angle is an acute angle. The dot product's positive. Function's increasing. So, in this case, if these three conditions happen, couldn't possibly be a maximizer. The function's still getting bigger. And the good news is, in most cases, for most of the points in your domain, these three conditions will all be satisfied most of the time. So, again, what we're going to call a critical point is just points where our argument fails. Points where, one of these functions fails to be differentiable and I can't do calculus. Well, that kills the argument. Points where the gradient is zero and then, then it doesn't define a direction and, the argument fails. Points where the gradient of f fails to not be a multiple of gradient g. In other words, where it is a multiple of gradient g, the argument fails. So, again, as we did in the unconstrained case, any point where any of these three things happens, we call it a critical point. We have no idea what's going on that point without taking a closer look, which is harder when you're talking about constrained optimization. But these are the points that we can't eliminate. These are the ones that we call critical points. These are the ones that might be the maximums that we're looking for. Okay, so examples of what we have left. I'm going to do as much as I can with these examples. These are just examples. Anyway, here we go. Example, we want to find the highest point on a certain surface with a certain equation. Claim this is a constrained optimization problem because highest means I want to make z as big as possible. Notice that my constraint is a level set. It's already written as a level set. I don't have to shuffle terms around. Specifically, I am looking at a level set of that function. So I've got my objective function. I've got my constraint function, and now we follow the rules. We play the game. Let's see, here it is. Step 1, do these functions ever fail to be differentiable? They're polynomials. Polynomials are always differentiable. No sweat. We have no differentiability critical points. Dead end there. No critical points down that road. Okay. Next. Where's the constraint gradient equal to 0? All right. Here's the constraint gradient. Bunch of partial derivatives. Golly, it's going to be a little hard to tell when that's going to be the 0 vector. Nice argument along these lines is to rewrite it like this. That's just a little bit of linear algebra here. Right? And having done so, if I now ask, okay, well, where is this equal to 0? Well, we have a Math 218 system of equations. And, various different ways that you can solve this. Now, I like to make non-singularity arguments. This matrix, it's easy to compute the determinant. It's non-zero, as it turns out. Just do the arithmetic, no big deal. Once you know you have a non-singular matrix, that means pivot in every row, pivot in every column. That means existence and uniqueness of solutions. That means I know there's exactly one solution. And hey, check it out. I know that x equals 0 is a solution, so that must be my only solution. Right? Is x equals 0. This is the only solution to the constraint gradient being 0. So it's going to be tempting to want to call this is what we would normally call a critical point. Here's the thing. Little subtlety here. This point is not on our constraint set. And remember, all we're interested in is looking at our constraint set and finding points on our constraint set that satisfy any one of these conditions right here. Well, critically, I'm only looking at points on my constraint set. If you find a point that satisfies one of these conditions way over here, who cares? I'm only interested in points that are on our constraint set. And what I have found here is not on our constraint set. It fails the constraint equation, so this is not a critical point. Does that make sense to everybody? Okay, so we toss it away. Okay. Lastly, the Lagrange equation. So gradient of f, a multiple of the gradient of g. So here's where the algebra gets a little weird. The gradient of f, the gradient of g. Here's what it means for the one to be a multiple of the other. Now I emphasize, it's real easy to make the mistake of just looking at these equations here, but remember, just like we just argued, the only reason I care about this happening is because when this happens on my constraint set, that would be a critical point. So, importantly, this is only important if it happens on the constraint set. And so what I really want to solve then is that combined with the constraint equation. I want to, in other words, find solutions to this great big purple system. Points that satisfy all four of these equations. Is everybody with me on that? And now begins the algebra. And every one of these is different. And it is what it is. So for whatever it's worth, I'm going to talk through as much as we can here, and then if y'all are interested, I'm going to stick around and talk about the remaining examples. We're not quite going to fit it in with the rest of the time. I'll also point out that the recording will keep going, so if you want to just check the recording later, that's also fine. And of course, in my earlier lecture, in my morning lecture today, I've talked through all three of these examples that I have here, so you can look at that recording as well. Anyway, that said, here we go. How are we going to solve this system of four nonlinear equations? And the answer is this: they can get hard. Right? Now, we will only give you examples where the algebra works out. Right? But it will remain that how that algebra works out will be different in every example. Now, here's the foot in the door with this one. If you look at this equation right here, let's ask the question, what can that lambda be? Well, it's not 0 because it's a factor of 1. So, lambda is definitely not 0. Is that cool? Okay. Well, if lambda is not 0, let's look at these two equations. With lambda being not 0, I can cancel a non-zero factor in each one of these equations. Perfectly legal to cancel non-zero factors. And that turns this then into that, which gives me this. I've basically solved for x and y in terms of z. Is everybody all right with that? Well, having done that, I can now plug that into my constraint equation, which turns into all of this, which you can then solve. It's just a great big equation for z, and out comes a value of z. And of course, once you know z, then you can solve for x and y from those green equations that we already found. Well, that's how this one worked out. Everybody on board? Sometimes it'll go like this. Now let me show you some other examples. Other examples how the algebra goes differently. I am going to skip through the preliminary stuff. Do make sure that always check differentiability. Always check for where the constraint gradient is 0. We've already done some of that. But let me show you where the algebra gets weird down below this line. Right, here's our system. We've got our Lagrange equations. We've got our constraint equation. How am I going to solve this system? What I'd like to do is solve for lambda in both of these equations and set them equal to each other. That would be nice. When this lambda's got equal to that lambda, and this gives me a nice relationship between x and y. That's wonderful. Why can't I do that? And tragically, I have to be careful with this because I don't know that I can cancel... Correction. I don't know that I can divide by x, cross divide, I guess you might say, that x into the denominator of the other side, because I don't know if it's 0, right? You cannot divide by 0. Underappreciated fact, right? If x is 0, then this is garbage, right? It's a nasty little sticky point. Okay, so first, I have to recognize that there's, in fact, no way that x or y could be 0. Just plug them in. See, those equations just flat fail right on their face. Right? You plug in x equals 0, the top equation, you get 1 equals 0. Unacceptable. So, you got to make that observation first, and having made that observation that x and y are non-zero, then you can cross-divide, if you will, effectively solving for lambda in both of those equations, and therefore that's equal to that, and therefore x is, well, let's see, I guess I'll do it like this, and therefore x is equal to negative y. Everybody see how that one worked out? And again, now once you have a foot in the door, it's all over but the shouting at this point. If x is equal to negative y, you put that into your constraint. Your constraint becomes this, and then this you can solve, and it's all over. Okay. All right, so that was a little different. Here's a third one. Again, don't forget to check differentiability. Again, don't forget to check when the constraint gradient is 0. Very important to make sure you check all the conditions. And with that said, here's the Lagrange conditions and the constraint equation. Now again, let's just focus on solving this system. Where it came from is the givens. But how would we solve this system? This is a really sticky one. lots of students would see a contradiction and say, oh, hey, check it out. Lambda has to equal to 1, but lambda also has to equal to 1/4. We're done here. Lambda can't simultaneously equal to both 1 and 1/4. So contradiction, therefore no solutions, therefore no critical points. Right? Everybody sees the allure of that, right? Nonsense. This right here does not say that lambda is equal to 1. It says either lambda equals 1 or x might be equal to 0. Right? If x is equal to 0, you cannot solve for lambda at all. Does that make sense? Does everybody see so this is the kind of thing that I believe, certainly in my high school, but I think a lot of high schools kind of sweep all this under the rug as, oh gosh, that's annoying and ugly and I don't want to deal with that. And then magically this kind of thing just kind of disappears from the class, right? When I was in high school, this kind of issue never came up, right? And this is a tragic problem because life does not care about the convenience of the algebra, right? So this is a real situation that totally comes up sometimes. So how do we deal with it? Well, we have to break it down into cases again. We'll start by considering the possibility that x is non-zero. Now, once you have x is non-zero, then you truly can cancel the x's. You truly can, therefore, solve for lambda and get lambda equals 1. And you truly can take this value of lambda equal to 1, plug it in there, and that makes y and z both 0 in these second and third equations. Everybody see what happened there? And once y and z are equal to 0, you can plug this into the constraint equation and get that x would have to equal to plus or minus 6. So what you got there is actually a couple of critical points, right? I mean, this is 2 critical points that we would have totally missed had we been a little too fast and loose with the cancellations, right? So please be very, very careful about that. And of course, there's these other 2 cases, where you know, y and then z. What if they're non-zero? And you get 2 more critical points in each case. So grand total, we have 6 critical points. And again, if we had just been a little too casual, we would have missed all 6 of them. So heads up, do be careful. Make sure not to divide by 0. Be careful with the subtleties of algebra. I'm going to point out, by the way, I have if you don't trust yourself on the algebraic sort of pitfalls and issues, I have a recording in my miscellaneous topics section called Algebraic Pitfalls. And it's all about this kind of thing. So feel free to take a look at that if you think it might be useful. We are now done with the material for the course. And so y'all have a good day. Thanks for sticking around a little extra. And see you for the exam on Wednesday. Good luck. Good luck on the final. Yeah, question?
Is this going to be on the exam?
It's all fair game. Yeah, that's right. Yep. Yes?
Why is the objective function x squared plus y squared plus z?
In this example? Well, because we wanted to find the points that are closest to the origin, and distance to the origin is square root of that. And then it's the same thing about, right, exactly. Yeah. Okay, see y'all later.